Imagine standing on a rooftop and reading the fine print on a business card a mile away. Not with binoculars, but by bouncing light off the card and using clever math to rebuild the letters. That image sounds like spy movie fantasy. But this month, a team of researchers demonstrated a technique that does almost exactly that. An active intensity interferometry system that reconstructed millimeter-scale text from 1.36 kilometers in outdoor tests. This is not a rumor. It is a published lab demonstration. And it comes with both enormous scientific promise and a real, uncomfortable privacy question. So let's start with the simple picture of what they actually did. Traditional long-range imaging tries to make a clean picture by collecting phase information, the detailed wavefront, but the atmosphere scrambles that phase, especially over long distances. Intensity interferometry takes a different tack. Instead of measuring phase directly, it measures correlations in the intensity of light at separated detectors and uses those correlations to reconstruct an image. Third, the technique currently depends on sophisticated post-processing and careful calibration of multiple emitters and detectors. It's not a plug-and-play device you can hide in a pocket. In short, powerful, yes, but not magic. That said, the applications are broad and exciting outside of espionage. Archaeologists might point an active interferometer at inaccessible cliff carvings and read weathered inscriptions without climbing. Conservationists could resolve small tags or micro-markers on animals from a safe distance. Remote inspectors could survey fragile historical facades or infrastructure features, cracks, tiny serial numbers, without physically visiting and risking damage. In the lab, the technique also promises to inform high-resolution optical sensing and metrology where long baselines are required. These are constructive, practical uses that can transform fieldwork. But the public conversation cannot ignore the risks, because the system achieves super-diffraction imaging by actively interrogating a scene with lasers and then reconstructing correlated intensity patterns. It reduces the barrier to resolving small details at a distance, details we normally assume are private in open-air environments. Journalistic and social coverage already flags the surveillance implications. Reading microtext or resolving identifying marks at a kilometer range opens obvious civil liberties and regulatory questions. Policymakers and technologists should not pretend this is purely academic. It is an applied technique that will be seized for both benign uses and for intrusive surveillance unless norms and rules are considered now. Technically speaking, why is active intensity interferometry robust against atmospheric turbulence? Because it relies on intensity correlations rather than fragile phase information. Phase scrambles easily as air moves. Intensity correlations are less sensitive to those scrambles across separated detectors. The active illumination further increases photon flux and improves signal-to-noise ratio in real outdoor conditions. Combine that with modern reconstruction algorithms, essentially huge inverse problems solved by optimized code, and you get a system that can see fine structure that would otherwise be blurred by the air column. That robustness is what makes kilometer-scale imaging feasible now. Of course, the devil is in the operational details. The current demonstrations use controlled test targets, letters, engineered patterns, and carefully synchronized emitter arrays. If you move to uncontrolled, complex real-world scenes, moving people, shiny objects, reflective surfaces, recovery becomes harder. Moreover, active illumination means the target receives laser energy. For some wavelengths and power levels, this raises safety and eye safety questions that must be managed. And because the reconstruction pipeline is computationally heavy, It requires both compute resources and expertise to tune. In short, the early demos are powerful proofs of principle, but substantial engineering remains before a robust field system can routinely read arbitrary tiny text at long range. Now let's pivot to governance. What should responsible policy look like? First, transparency and public debate. Academic labs and companies should disclose capabilities and limitations early, not after commercial or military deployment. Second, usage constraints. Active long-range interrogation of private property without consent should be explicitly regulated. Third, export and procurement rules could be considered for systems with the clear potential for intrusive surveillance. Finally, dual-use research needs careful review. Promising archaeological or ecological projects can be enabled while minimizing pathways to misuse. This is the kind of technology where technical nuance matters for regulation. A blanket ban would also block valuable science. But neither can we sit back and hope market norms will self-police. There's also a global diplomacy angle. As different countries push long-range sensing, norms about acceptable behavior in open skies will be tested. International law already governs some aerial surveillance and satellite imagery, but a laser-based ground-to-ground interrogation technique sits in a gray area. It's not a satellite, it's not just optics. Multilateral dialogue among scientific bodies, privacy advocates, and regulatory agencies should begin now to define acceptable usage, technical safety standards, and transparency requirements for field deployments. The technology should not outpace the rules we use to hold it in check. Let me be honest about the timeline. The physics community has been talking about intensity-interferometry concepts for decades. What changed is a pragmatic engineering turn. Better lasers, synchronized emitter arrays, more sensitive detectors, and orders of magnitude more compute for reconstruction. The paper and demonstrations published this year show the technique is moving from concept to soil-tested prototype. Expect incremental improvements, tighter emitter control, AI-assisted reconstruction, faster hardware, in the next 2 to 5 years that push the method into more robust field tools. That's fast in physics terms, slower in regulatory terms. So what should you take away from this? Beyond the coolness factor. First, this is a legitimate optical breakthrough that expands what we can resolve at long distances in real-world conditions. Second, it is not an all-seeing superweapon today. It has limits and safety concerns, but it lowers the bar for intrusive surveillance in ways that require attention. Third, the technology's best uses are constructive, archaeology, ecology, infrastructure inspection. And we should accelerate those while building guardrails for privacy and safety. That balance of optimism and caution is the practical stance scientists and citizens should adopt. If you want to dig deeper, start with the research paper and the lab's experimental materials. They explain the emitter geometry, the correlation math, and the reconstruction algorithms in transparent technical detail. And if you care about policy, follow the emerging conversations in tech and privacy forums. This is exactly the moment to ask what societies will allow when capability arrives faster than regulation. Finally, if you thought this was a spy story, you were half right. It reads like one. But it also reads like a tool that could help archaeologists read lost cliff inscriptions without ropes, help biologists monitor tiny tags on animals without disturbance, and help engineers inspect infrastructure more safely. If this episode landed for you, hit subscribe so you don't miss our follow-ups. I'll do a technical deep dive on the math behind intensity interferometry and a policy episode that sketches concrete rules for responsible use. Drop a comment. Should this tech be restricted, licensed, or openly shared with public bodies? I'll pin the best argument and bring experts into the conversation. Tonight's takeaway is clear. Active intensity interferometry pushes long-range imaging into new territory. Exciting for science, useful in the field, and politically urgent. The future will be shaped not just by lasers and algorithms, but by the choices we make about how to use them.